large numerical models like TabPFN3. But what are they? Large numerical models, or LNMs, are state-of-the-art, in fact transformer-based models which has been designed for supervised classification and regression tasks. But the thing is, why are they important? Because we have large language models already, and what are these numerical models one for? So the thing is, I was watching a video about one of these CEOs of LLM companies, he was arguing that we need to get to the state that we can have artificial superintelligence, because if we get there, so technically artificial superintelligence can help us to solve lots of open problems like, I don't know, energy problem, hunger problem, so on and so forth. So that's why it's very important to work on large language models to get to the superintelligence state. But what I would say I slightly disagree, and the reason for that is because, as we know, Einstein says the whole universe and the world speaks in mathematics, and I do agree with that. So universe speaks in mathematics and rules of physics, and technically, as a result, data and numerical data. So I would say a language model which speaks in English, German, or Persian, or whatever, cannot necessarily solve a problem like, I don't know, energy problem, because at the end of the day, these are all kind of physical models which they don't speak in English, they do speak in numbers. So that's why it's important to make models which are good at mathematics and numbers. So when they can look at a bunch of numbers or numerics, they can think and in their context say, this is a pattern that I see in this data, not just a language like English or so on and so forth. So yeah, but what is the difference of them with other, I don't know, machine learning algorithms? So unlike traditional models, which has been, for example, designed for tabular data like XGBoost or, I don't know, tree-based models, it does not need this large numerical models. They don't need any training. So what do they do is we train them on a large amount of synthetic data, which I get there in a minute, and then from that they learn how to recognize patterns in the context, and then they, as soon as you give them a dataset, they can infer the relations and just give you the labels of the test data. So yeah, how they work and what they've been trained on. So technically they've been trained, as I said, they've been trained on synthetic data. Just again, back to what Einstein says, or any kind of, I would say, natural event has a distribution. And if we find a distribution, we can kind of model that natural event. So the thing is, by synthetic data, we can mean a kind of prior distribution. So we need to make lots of distributions and give them to the model, and then model can see, I don't know, hundreds of millions or billions of synthetic data, let's say distributions. So they are really good at detecting pattern. But the thing is, it shouldn't just necessarily be any kind of distribution, because in real world we do have relations in that distribution. Distribution is not random. They have consequences, they have, I don't know, actions and reactions, they have, I don't know, correlations, so on and so forth. So we need to design the priors in a way that they are very logical, and then we can technically give lots of these distributions to the model, and they can learn, and then once we give a new dataset, they can infer and find out the relation of that data, and then give us the labels. Okay, now let's quickly go and have a high overview of this TabPFN3, which is technically one of the, I would say, most famous large numerical models, and I think in Tab Arena benchmark they should be the first or the second or something like that. So yeah, okay, what TabPFN3 is and how it works, a very high overview of it. So it has I would say 9 stages, 9 main stages, from the time that we have the raw input all the way up to the many class decoder. So at the first stage, or let's say stage 0, we have the raw input. So technically the model takes in a batch of tabular data formatted as a grid of rows and columns, and then I don't know, some columns may contain known class labels, so on and so forth, and others they could be, I don't know, even the missing values, just like any kind of tabular data that you might have seen during your career or whatever. So yeah, so what it does, it sees them as a kind of unified sequence to be processed together rather than an isolated, I would say, data points. And when we say sequence of data, remember that, so for example, in the large language models, what we have something like positional encoding or rotary positional encoding in order to encode the position of each token, because tokens and the time that they occur, the sequence and the timing is really important. But in a tabular data, other than time series, we don't really care, because technically they could be samples which has been sampled at any time, so we don't really care which record is in which row of an Excel or a CSV sheet. So most of the time for tabular data, other than time series, we don't really care what is the sequence of occurrences, and even in the features as well, because features are just, they might have some relation with each other, but the sequence of them are not necessarily very important. So the second step would be, I'm gonna go a little bit more detail into each of the steps, but first, yeah, let's have a very high overview. The first step would be just a feature expansion and embedding. So see it as at each layer we have, I don't know, let's say each row we have different values, so which we need to embed them into a space, try to gather as much information as possible, and also at the other hand we need to extract some information from the labels of the training data. So we embed them and, I don't know, do some calculation on them and try to get some information out of them. So that was technically stage 1 and 2, which we can call it feature expansion and embedding, and also column by encoding. And also it's important to note that we can kind of expand the features in fact for the real values other than labels, but I will get into that in a minute. Stage 3, it is mainly feature distribution, comparison, that's what are the features, what do they do, what is the distribution of this feature in the whole dataset, and yeah, so on and so forth. We also have column aggregation. So technically what we do is we do see what each feature, what's the distribution of each feature, and then we try to understand what is the distribution of the whole dataset. So by doing these 2 steps, we can understand that, okay, what is each feature likely to be and how the whole dataset is going to be, or it is. And then we have a stage 5, which is called ICL label encoding, and by ICL we mean in fact in context learning, because if you think about it, it's kind of important to have in context learning, because we don't do any training. The way that the model works is that it is seen a lot of millions and millions or even billions of synthetic data, nicely selected prior synthetic data, and then it knows on the runtime that when you give it data, it can immediately infer and understand the pattern in the data set and then give you the labels for the test data. So that's what in context learning means. So for example, when you give let's say working with ChatGPT or Claude, when you give an example in the context or in the prompt, it can literally understand it and learn it on the fly. So this is technically in very high high level and high overview. This is what in-context learning means. And then we have in-context input assembly. The model constructs the final comprehensive state of each individual row by, I don't know, combining the global dataset fingerprint. Yeah, we can call it something like that. Then we have stage 7, which is in-context learning blocks. So technically we have a bunch of transformer decoders which they try to learn something and understand. So this is the core reasoning engine where the actual learning takes place without any traditional parameter updates, and it is kind of through stacked transformer blocks, featuring dynamics. And then we have output normalization and test, I would say slicing. And also it might worth mentioning that in the attention mechanism we do not attend to the test labels. We will get into that in a minute. And then we have a many class decoder, which instead of using a traditional fixed classification head, the model operates like a sophisticated nearest neighbor classifier by projecting the test row's final vector and comparing it against land prototype vectors for every possible class. Okay, let's now go to a little bit more detail, but it's still high overview, and if you want to see more in-depth and have more in-depth understanding of it, technically go to the paper. And also I will share some information, slides, a PDF which is really, I would say, in-depth a numerical example of that. Okay, let's imagine this is a dataset from iris, I think, flowers. Imagine that we have that kind of tabular data. What happens if we have 4 training samples and 1 test, and how that happens, and what happens if we give that to the model? What would be the whole cycle of the training and or inference? So I will put all these into the link in the description, and you can go and have a look at how it works. But imagine that this is our data from iris dataset. So we have row index, we have data values up here, and we have also class labels. So the data values, as you can see, a bunch of numerics. Then we have class labels. We have 4 training data points, and we have 1 test. And as you can see, these are our learned parameters. So we have a batch of 1 rows, number of rows 5 for training, 1 for test. Features, we have 3 features, as you can see, 3 feature columns. And number of classes, let's say those are 3. So the shape of the data would be 5 by 3 matrix. Okay, what we do next? So technically from each value over here, let's say 5.1, we need to extract some more information. We need to kind of embed them, and just like tokens, see them as tokens. We need to understand them more and get more information from them. So what in this paper they do is they're gonna expand it. And what do they mean by expanding? Because one possibility is that we might have missing values. Okay, how we should recognize that this value is a missing value? By expanding it. But what we mean by expanding it? So each value in the dataset, or each cell in our matrix, will be turned into a vector of 6. And what is the vector of 6? So let's say that 5.1, we have the value of the cell. We have another value in the second place which says, is it a nan or not? So it would be 0 or 1. So in this case we have the value, so it would be 1. So the first one is 5.1, the second one is 1, because the value is clear. So the third one will be the I think the cell value to the power of 2. So 5.1 to the power of 2. The next one is 5.1 to the power of 3. This is technically to give the model more understanding of what is the scale of how big or different the numbers are. The next value, the fifth place, is the logarithmic value of the cell, and the last one is the sign of the value. So in this case it is positive, which would be again 0 or 1. Then we're gonna give it to a linear projection. We're gonna kind of embed them into a I believe 48 dimension. We can say 48 dimension, it doesn't matter really. These are all parameters which can be changed in the config file. If you go to the TabPFN3 GitHub repo, you can find all those variables. If I want to explain a little bit in more detail, or maybe mathematically, so we have the raw data input features. As you can see, all of the data that we have batch, number of features, and number of rows and number of the features. So we have 1 by 5 by 3, and this is how it looks, and this is technically the labels for us. Then we have NaN expansion, as I said, so we have the value, we have if it is NaN, to the power of 2, to the power of 3, logarithmic value, and the sign value. So each individual number here will be turned into a vector of 6, and yeah, as you can see here. And then we're gonna do that embedding, which we saw here, the linear projection. Then that would give us a vector of 48. So here at the beginning we had 5 by 3 matrix. Now each of these values all by themselves are a vector of 48. So that would be 5 by 3 by 48, I believe. Yeah, as you can see here. What is next? Next, we need to extract some information from the labels. We extracted the information from the values. Now it's time to extract information from the labels. So we have something called induced, in fact, vectors, which technically, if I go back again, so I think it should be somewhere around here. Give me a second to find it. Are we first doing the yeah, technically no, we're not gonna do the induced vectors at this stage. So what it does, the way that model works, that let's say there is another learned or learning matrix which is 160 by 48, and each of these 160 are different labels. So the thing is, this is a fixed sized matrix and it won't change in any of the training, in any point of the training, no matter how many classes your dataset has, it will stay 160. In our case we have 3 classes, so we're gonna just take care and take advantage of 3 of those 160, and it kind of gives us a limit that, but this is also a hyperparameter which can be changed in the config file. So this would technically give us how many classes generally we think our world might has. So it is 160 in this case. And also, if you think from your experience or whatever, there are few datasets, not many datasets in terms of classification, not regression, that they have more than 160 classes, but this can be changed. But so for this example, at least we have 160. So what we do during the whole training, all these 160 technically, I would say rows, they're gonna be learned, and these are technically classes. So then we have feature blocks, we have label blocks. We're gonna, and because again it's a 160 to 48, each class is again a 48 dimension vector. So we can technically add them together and get a new vector. The reason that we do why embedding and added on top of the feature block is because we want our, so for example, back again into here, we want each of these values be aware and understand and have, and has information about the label. We want them carry information about themselves, but we also want them to carry information about the class that they kind of represent. That's why we do the summation, and then once we have that, so we just do the rest of the work. And what is the next? I would say I can go here, but maybe we can do it from this side. So once we added those, in fact, labels on top of the values, now we need to understand what is the feature space look like. So back to here. We know what this value is. What is the characteristic of this value? Is it negative, a huge number? Is it a nan? Yes, no, whatever. We embedded that, get some information. We also added some information of the label on top of it. So it has all the information about what it is, what label it has, but we still don't know what's the relation of this value compared to the whole column. So when I say, for example, let's say, I don't know, someone in UK or in London is, I don't know, 160 centimeters. Does that tall? Is it tall? Is it short? We don't know, but we know it's 160. When we can say that that guy is tall, when we have information about the whole population, or at least a sample of population. So that's why we need to understand the whole population, and then based on that we can also add that information into each of those values. So then if you tell me that the mean value, I don't know, mean height for person in London is 180, so then I might say that guy is relatively short. But if you say it's 150, then I can say that guy is relatively tall. So that's what this feature-wise distribution is. So we just do a quick kind of swap here. So we had 5, 3, 48, we do 3, 5, 48, and the reason for that is because we want to do a bunch of calculation. And the way that we do that calculation, we have something called induced vectors. What are the induced vectors? Let's go back here. From your experience, statistics, math, science. If I want to tell you that, okay, how would you describe this column? What would you say? If I say, describe this column, so you might ask a couple of questions, and based on those questions, you can tell me that what this column would tell me. So those questions might be, what is the mean value of that? What is the variance? What is the, I don't know, the maximum and minimum? And so on and so forth. So these induced vectors are exactly like those questions. These induced vectors are learned parameters which try to extract as much as data from the feature columns. And once we have them, we can also add them back into the dataset, the values, and then once we have all that data, so what we have right now, imagine it, at each value we have the value itself. What is that value? We have information of the label. We also have the information of the column. Now it's time to get into the attention blocks. So we do a kind of attention mechanism here. This attention mechanism will help us to extract some more information out of, technically just like any other attention mechanism, it helps us to extract information from data set. And so that was mainly for the what was the name again, the feature extraction part. And then we're gonna do the same thing for a column aggregator and data fingerprint. So what we said that, okay, I know what this feature looks like, and I know what is this value and the position of this value in this column. I extract it and I add it back to this value, but I still don't know how this guy is compared to the whole dataset. So what column aggregator and data fingerprint does is exactly that. So what we have, we were gonna add two more tokens, two more, let's say, vectors, C0 and C1, CLS tokens. What do they do is they literally, so previously we had three features, 1, 2, 3. We add two more, as you can see here. Then we have 5 by 48. And then we do a kind of rotary positional encoding on top of that in order to just make sure that the sequence has kind of ordering. CLS token 1, CLS token 2, first feature, second feature, and the third feature. And then on top of that, so these two guys are learnable parameters, and what they're gonna do, they're gonna extract and summarize all the information from the whole dataset. And in order to do that, what we do, technically we do a attention mechanism. We're gonna see that how much C0 attends to each of the tokens and how much information it can extract from them, and also C1. Once they are learned, as we said, the vectors are 48. So we have two vectors of 48. We concatenate them, so we end up with a vector of 96. So in general, this is the shape that we have, and this guy here will tell us that what the whole data set looks like. We add it back into on top of the in fact our own architecture, and once we have that, so technically what happens from now on is kind of more transformer, because I would say this was the main part. We know the values, we extract information from them, we add information from the labels into them, we add information of what is their relation or position compared to the whole feature, and also the whole data set. So once we add all that information, we are good to go to do our, further in context learning, because we literally extracted as much as data and information as we could. So this also is available in the link in the description, you can check it. So yeah, we had X row, we had Y row, we embedded them, the non-values, embedding, broadcast the label dataset, labels, features, reshape them, the induced vectors, extract all the information out of them, give them into the next bit, which is another, technically, as we said, column aggregator. Column aggregator will extract information at the more dataset layer. Then we have all that information. We have two more, I would say, transformer layer in order to do the in-context learning, because now we have all the features that we want. And then once all that happened, we can do our own kind of classification. But what is important here, as you can see in a normal transformer or attention mechanism, we do Q times K transport over the square root of the model. But pay attention, at each of these blocks in the feature distribution and column aggregator, we have two layers, as you can see, two attention, let's say, layers. The first one, usually this one and this one, the part which is the model is not a fixed number, it is also a learned parameter. And the reason that, based on what I understand from the paper, the reason that offers does that, they think that they can extract more information from each feature or column by doing that, rather than having a fixed number, which we might lose information and we might not kind of normalize the data in a right way. So the first attention mechanism at each block, the D model, is also a learned parameter, but the second one is a fixed number. And yeah, I would say that's it. That's a very kind of high overview of how the whole architecture looks like and works. The main thing is it has in-context learning, and that's the whole idea, because we don't want to do any training. If we do the training, technically that would be a neural net, but we don't want to do that. We want to give the data, tabular data, and boom, get the labels. That's it. Just like a language model. We don't want to pre-train at each query. We want them give us the answer right away. There's also this numerical, example here, which you can go and have a look. I will put the link in the description. The whole architecture, literally this is from a run in TensorBoard, how exactly each of the blocks look like and what is the dimension. And yeah, that's it, I would say, for now. Thank you very much.